So I'm going to tell you a lot about black holes, some myths, but first I want to tell you how we learned about them in the first place. And that story begins a long time ago when people did not know what galaxies were, for example. No idea what black holes were, no idea even really what stars were at the time. And people looked up in the sky and they saw that sometimes stars were collected together, like nebula. And at the time, we didn't know that this was, a word for nebula didn't mean anything. All people meant when they said the word nebula was sort of like glob of stuff in space, not individual points. And with powerful enough telescopes, we were able to resolve that those globs of stuff were made up by smaller points. These are what we now call galaxies. And so here's a great photo from 1899 of Andromeda, our neighbor galaxy. And as you can see, it was titled the Great Andromeda Nebula. So we did not at that time know what it was. And some very interesting things about nebula. For a minute, I'm going to jump ahead to about the 1950s, when people looked at nebula, when people looked at the sky and with radio telescopes, and they saw strange radio signals. And if they pointed powerful optical telescopes at them, such as the Hubble Space Telescope, this is what an image of that, it looked like a star. But stars don't make radio sounds, quote unquote, make radio waves the way that these things do. So they were just called quasi-stellar objects, or quasars for short. But even way back when, jumping back in time again now to the 1800s, when people looked at these nebula, they often saw some crazy stuff. So for example, here's a wonderful description of a nebula from back then: two semi-ovals with elliptically formed nebula appearing to be cut asunder and separated by a broad, obscure band parallel to the larger axis of the nebula, in the midst of which a faint streak of light parallel to the sides of the cut appears. So what John Herschel was describing, we now know is something called an ultra-relativistic jet. And I'll tell you more about what that is. It's coming from a black hole. And this is a picture of that happening. So this is another galaxy. That's the brown stuff down along the center, that's a galaxy. And then this stuff blowing out perpendicular to it, that is this jet. And this is being produced by a black hole at the center of the galaxy, and it's way, way, way bigger than the black hole or the galaxy itself. This jet extends beyond the size of the galaxy. And so what this might tell you is that that black holes can have huge, very powerful effects on their environments. They might play a key role in how galaxies evolve and form. We now know, of course, that galaxies are collections of stars, not a single blob of stuff. So people, of course, what about our own galaxy? And it turns out that we can look at our own galaxy. Our own galaxy contains something like a quasar, although we don't see this powerful jet of material. And so people looked at the center of our galaxy, which has a strong radio source, and they tracked the stars around the center. So that's what this movie is showing. So each of those dots is a star, actually tracked with telescopes. And then the star, the shaped thing at the center, is named Sagittarius A star. And it's the thing at the very center of our galaxy. And as you can see, the actual stars are orbiting around it. Each one, some coming closer than others, but they're all orbiting. And it turns out if you track how massive that thing at the center has to be to drive those orbits of each of those stars, and if you, then it has to be something like 1 million times the mass of the sun. And if you track how close things are getting to it, there's no way, like that inner star, the orange orbit, there's absolutely no way that that thing could get that close to Sagittarius A star if Sagittarius A star were as wide as you might expect for like a ball of gas that massive. And that's what told us, this was the first real evidence we had that black holes are real, because the thing in the center is way too dense to be a star, and it's really, really massive. So it is the first piece, this is the first supermassive black hole that we knew about, is our own neighbor. There's many other ways that black holes appear. For example, there's these things called X-ray binaries. This is when you have a black hole and a star that are orbiting each other, and the black hole is slowly eating the star. It's a very messy eater, and so together, the whole binary together glows very brightly. We call this an X-ray binary. And this is an amazing ALMA photo of that system, or one such system. And of course, now we're all pretty familiar with gravitational waves, but I remember as a graduate student in 2015, when these were discovered, it was hugely exciting. Basically, no one could contain their excitement for weeks before or after the announcement. And what happens here is that if you have two black holes orbiting each other, and they emit gravitational waves, distortions in space-time. And as those gravitational waves, as the black holes get closer and closer together, those gravitational waves become more and more intense, and the frequency goes up. And you can actually translate the waves, these distortions in space-time, into a sound, and it's audible. It sounds like this. And we've now detected a huge number of them through the gravitational wave detectors from LIGO and Virgo. And the predictions that these things are gravitational waves, these gravitational waves are produced by black holes matches beautifully to the data. So we're very confident that that's what these things are. And here's a movie of this. So from LIGO. So there's two black holes in spiral and merge. This distortion of space and time passes through the universe, eventually through us, and distorts the Earth itself. And that's how gravitational wave detectors work. They detect these distortions because the Earth is stretched and shrunk, and it's a very incredibly tiny effect, but if you have a sensitive enough detector, you can detect it. So let's talk about what black holes are and how they work. You're probably familiar with maybe familiar with this picture from the movie Interstellar. And you know, this picture looks really crazy, but it's real. Well, that particular black hole is not real, but the crazy rings of light and all this stuff going on here, that is real. So let's talk about this a little bit. So you'll notice that the light stops at some point as you go close enough to the black hole. And that is because that's the event horizon. When you get close enough to a black hole, it's the gravity of it is so powerful that not even light can escape. And so the point where it goes dark is the point where light stops being able to escape from the black hole. But if you go a little bit further out from that, well, light can actually be distorted and bent. And so it's that ring of light that you see just outside of that is light orbiting the black hole, stuck in a circular orbit the same way that the Earth orbits the sun. And what about all this? What about the rest of this light, like the glowing disk stuff? I'll get to that. So, but before that, I think it's time to bust a myth. So what if the sun turned into a black hole? You might expect that we might get sucked in or something, but actually no. If you take the sun and make it a black hole the mass of the sun, then well, we'll get cold because there won't be any more light. But the sun isn't, the black hole isn't a massive vacuum cleaner. It has exactly the same amount of gravitational pull at the distance that we are as the sun would. The only difference is that it's a lot smaller. And if you get too close, the strength of gravity is the strength of gravity about black holes being so strong light can't escape. It's not really about the strength of the black hole. It's about how close you get, because gravity is stronger the closer you are to something. You can get way closer to a black hole than you can our own sun. Because if you tried to get that close to the sun, you'd burn up. So another amazing thing about black holes is that they can be mined for energy. And it's not maybe as crazy as you might think. Imagine that you have, well, imagine you're spinning around like this guy who's about to throw this ball. And when he launches this ball, he's turning his rotation, the spin that he's using, into motion and energy for the ball. It turns out that you can do very much the same thing with black holes. If you get close to a black holes are spinning, and they're spinning so fast that they're dragging space and time with them. And if you get close enough, but not so close you fall in, you can take advantage of that spin. And you can go near, pick up a lot of speed, and then go out. And it turns out that you can design a theoretical system to use that to power something. So this is called the Penrose process. You might also imagine that black holes are extremely dark. For example, I told you that light never escapes from them. But this isn't actually true. Black holes themselves are dark, but their environments are incredibly bright. And this is because of the stuff falling into them. So what I'm showing you here is what's called an accretion disk. Let me see if there it goes, it's restarting. From a big supercomputer simulation that I ran. And what's happening here is that you have material that's orbiting the black hole. And with time, that orbit, for reasons having to do with the gas and the material, that orbit decays. And the material falls in and forms this sort of disk of material that's slowly falling in. And as it does so, it heats up. And because it heats up, it glows very, very brightly. And so this is why we can detect, for example, X-ray binaries. Another thing that's really incredible about this is, I mentioned those ultra-relativistic jets before. In this simulation, you can see the ultra-relativistic jet actually form. So the above and below the black hole, there's not very much material. And that absence of material is because powerful magnetic fields in the accretion disk push all the material away and accelerate it to extremely high speeds. That is the ultra-relativistic jet. And the ultra-relativistic jet also glows incredibly brightly. Let's go back to that interstellar picture, although this is not interstellar, where you notice that there was like this weird effect where you could kind of see like there was this ring of light that was bent up like you see here. That is the accretion disk. The stuff that's sort of in front of the black hole, that's the accretion disk between you and the black hole. What about the stuff above? That's actually behind the black hole. What's happening is that the light emitted by that material is getting bent by the power of the gravitational pull of the black hole so that it points at us. This is called gravitational lensing for kind of obvious reasons. The gravitational pull of a black hole is so powerful that it can literally distort and magnify or shape the image of what you see. And of course, given all of what I just described, I would be remiss to not show you the most recent and most exciting piece of evidence we have that black holes exist, which is a real picture of one. So this is an image of the black hole at the center of the galaxy M87, produced by the Event Horizon Telescope, which is actually many, many telescopes across the planet linked together to get enough power to actually see what this is. And this, you might recognize some pieces of this image. That ring of red around it, that is the glow of this disk of material falling into the black hole. And the reason that it's yellower on the bottom than above is because that material is moving towards us and that means it's brighter. The center bit where it's black, somewhere in there is the event horizon, which is why we don't see any light from that. So let's talk about another thing about black holes that maybe you saw in the movie Interstellar, maybe not. Certainly you've maybe heard of that when you get close to a black hole, time slows down. So what's really going on there? Let's dissect this. And we're going to do it with a thought experiment based on some of the characters from Interstellar. So suppose you have, well, now I'm blanking on their names. We will just call her Astronaut 1. So suppose Astronaut 1 is far from the black hole. And Astronaut 2 is at the same place as Astronaut 1, but he starts to fall in. And as he falls in, at each moment, he shines a light, like a flashlight or something, up at Astronaut 1 so that she can see him. He does this every second. But as he falls in, he continues to do this. But as he gets closer and closer to the black hole, it gets harder and harder for the light to escape. And so, even though the Astronaut 2 doesn't notice any difference in the flow of time, the images of Astronaut 2 that Astronaut 1 sees get further and further apart because the light emitted by Astronaut 1 takes longer and longer and longer to get to Astronaut 2. This is really what is going on behind the time dilation that you've heard about in black holes. Black holes are, you can think of this as a warping of space and time and time stretching out. But you can also think of it more easily as just what happens if it takes light longer to get to you. So where do black holes come from? Well, it depends. The black hole, there's kind of two kinds of black holes, as I've kind of already suggested. There's black holes that are really enormous, like the ones at the centers of our galaxies. These are supermassive black holes, millions of times the mass of our sun. There are also black holes out in the universe, some of the ones detected by LIGO, these X-ray binary things, where the black hole is more like 10 to 100 times the mass of our sun. In fact, maybe 5 to 100 times the mass of our sun. So those black holes, these so-called stellar mass black holes, stellar mass meaning not a million times more massive, come from the death of stars. So when a star dies, the core of the star, it runs out of nuclear fuel and it collapses. And in the process of that, there's often a huge explosion called a core collapse supernova. At the end of that, what you get is something, either a black hole, which we've been talking about, or a neutron star, which is kind of this related thing. I'm not going to talk about it now, but we can talk about it in the questions section if you'd like. Ask me about it if you're curious. And at the end of it, one way we know that this happens is that we can see the leftovers from some explosions. So on the left, I'm showing a computer simulation of an explosion like this. On the right, I'm showing an image of a real, I guess, corpse of a star. So that is the Cat's Eye Nebula. It's also my background. And that is the remnants, what that glowing stuff is, that beautiful structure, that is all the gas blown off by the explosion, slowly expanding away. And at the very center of that, there's the core of the star still there, left over from the explosion. In the case of the Cat's Eye Nebula, it's a neutron star, but we know very well that for many of these things, it's a black hole. But what about these supermassive black holes, like the one that's producing this giant jet in this galaxy that I showed you before? Well, we actually don't know. This is a huge open science question and a great mystery. We know that we don't actually understand how they can get so massive since their formation and when they formed, because they must have formed very early in the universe to get as massive as they are. But even if they formed at the earliest points, we don't understand how they can grow quickly enough to be as massive as they are. And it's believed that they might evolve in tandem with their host galaxies, and that these supermassive black holes might be a really key piece of how galaxies themselves form. If you watched Aichi and Eicheltop's talks before on PEEC, then you might have heard her talk about this. This is actually her research area. So at that point, I left lots of time for questions. I just want to summarize what we've learned, and then let's have a conversation. Black holes are real. We know this because of quasars, X-ray binaries, gravitational waves, and most recently the Event Horizon Telescope. They aren't vacuum cleaners. They can be mined for energy. Time dilation has to do with how long it takes light to get away from a black hole, and they can bend light. So at that point, let's talk. Hope you all have some questions.
Okay, thanks, Jonah. So if you have any question, please type into the chat. So there's the one question. Can you use black holes for time travel?
That is a great question. And the answer is a little bit complicated. So for real black holes in space, probably not. But there are theoretical models of black holes where this does work. So there are, if you have a black hole, for example, that is so-called extremal, meaning that it's spinning so fast that all of the energy contained in it, like E equals mc squared, means that you can convert energy to mass and vice versa. There's an amount of rotational energy. If it has more rotational energy, if all of its mass is tied up in rotational energy, which is kind of a crazy thing to say, then the event horizon disappears, and you can go near the horizon, and you can go near the singularity. And in that region, you can, in fact, travel back in time. But this is probably not real. It's really a theoretical thing.
Okay, next question is, how many black hole mergers have been detected?
That is an excellent question, which I should know the answer to off the top of my head, but I don't. But at this point, it's dozens. Hyun, do you know off the top of your head?
So I don't remember the exact number of the black hole mergers, but the LIGO can detect gravitational wave also from the neutron stars or black hole neutron star merger. So the latest confirmed number LIGO detect gravitational wave is 50. So I would assume that more than like a 35 is black hole merger.
Yeah, that sounds about right.
Mm-hmm. So the next question is the time dilation in interstellar realistic?
Yeah, that's a great question too. Yes and no. So the fact that time dilation was there is realistic. And they set up the black hole so that the time dilation sort of per planet, you know, they go to a specific planet and it's like 1 hour there is like 7 hours in space or something, or I think it was even more extreme. You can get that in, like, they put the planet close enough to the black hole that is realistic. But the fact that the planet was that close to the black hole is probably not realistic. So yes and no.
So another chat question. Thank you for the very informative. So where in the picture you showed is the star's core?
Okay, I might need more clarification on this. Are you referring? I think you're referring to this picture here.
Yeah.
So on the left, it is. Can I make like a? I don't know how to do this. Can I draw on my screen or something? Or can you? I'm not sure. But oh, here we go. Annotate. Spotlight. Let's try this. So I don't know if you can see this or not. But the red sphere at the center of the left picture is that red sphere there is the core of the star in the simulation. As for the Cat's Eye Nebula, it's somewhere in the center, like but I don't know if it's exactly in the center. It's hard to know. Does that answer your question?
I'm waiting the replies. In the meantime, so another question is, how many black holes are expected to be in our galaxy?
Oh, that's a really good question. I don't know the I don't know the answer to that. I would think that there's quite a few, but there's every star above a certain mass is going to form a black hole pretty much when it dies, and I don't know I don't know off the top of my head. Let me get back to that question. I will try to do some math in my head while we're talking. If I don't get back to it, Hyun, remind me.
Yeah. Okay. So, and then also that was the question about the star core. A quick question related about this picture. Isn't that really the Crab Nebula?
Yes, sorry. I always mix up crab and cat's eye in my head because they're the two most beautiful ones.
Okay. So another question is, what about white holes?
Oh, yeah. So white holes are this sort of theoretical concept. They come from the mathematics of black holes, where if you take the simplest model of a black hole that we have mathematically is one that has existed forever. This is a physics assumption. It's like a spherical cow. And if you make this assumption, which is wrong, it's made up, it turns out that the mathematical solution for these black holes predicts a symmetric partner to the black hole, which is sort of its time reversal, which is a white hole where stuff can only come out but never go in. And you can even construct these sort of elaborate systems where if you have a spinning black hole, then like it can form a wormhole where the black hole feeds into the white hole. But these make an assumption that isn't real, which is that these black holes have existed forever. If you don't make that assumption, there's no reason to believe that white holes should exist or wormholes. And in fact, there, I think, are very good reasons why they can't exist, because if they did, they would be sort of injecting chaos into our universe in a way that they would undermine the ability to predict what happens, because you can't predict what comes out of a white hole.
So I think that the question is a consequence about the previous white hole. So are wormholes between black holes and white holes a myth?
Yeah. Yes. So I think so. The wormhole between them kind of depends on this assumption of the black hole having existed forever, and that doesn't seem to be true.
So, okay. So another question is, will the stars you showed earlier be swallowed by M87?
Yeah, so M87 was our neighbor. M87 is the galaxy that's hosting the black hole that was imaged by the Event Horizon Telescope. You're probably thinking of this movie, which is Sagittarius A star. Most of these stars are on stable orbits, so they won't be swallowed. But once in a while, one of these stars makes a really close pass towards a black hole. Also, this black hole at the center of our galaxy is called Sagittarius A star. And when that happens, it gets ripped apart by the gravitational force of the black hole. And this is called, astronomers have very boring names for incredibly cool things. These are called tidal disruption events. And one of these happened a couple years ago for Sagittarius A star. There was, I think this was like 2014 or something. You might have remembered the news about like astronomers are watching a black hole eat a star. That was this. A star got too close to our supermassive black hole and was torn apart. By the way, going back to the question about how many black holes are in our galaxy, I would guess tens of billions, I think, or you know, at least a billion. That's my guess. I do not know the answer for real, but that's kind of my back of the envelope estimate. And this is coming from the fact that there's roughly 400 billion stars, and when a star dies, if it's very massive, it forms a black hole. So kind of dividing by like, well, some of the stars have to have died, and not all of the dead stars are going to form black holes. So roughly a billion, but it's probably a bit less than that.
Okay, so another one. Can you measure the age of the black holes?
Can you measure the age of black holes? Not really. This is really hard. The way that we measure the ages of stars, Joyce, who asked one of the questions already, knows how to do this very well because she kind of does it for a living. Is you look at their color and you kind of can infer the type of star and how old it is, because they change how they look over the course of their lives. For black holes, that's not true. They always look the same, except that they're more or less massive. So the game of trying to figure out how old a black hole is kind of comes down to if it's a given mass, how long would it have taken, like how old of a star would it have needed to be to, like how big of a star would it have needed to be when it died, or if it's a supermassive black hole, how long would it have taken to eat enough material to get so incredibly massive? But it's really, I mean, it's big open questions there. We really don't know how old black holes are. I guess one key maybe is that the LIGO black holes, we know how long it takes for orbits to decay. So if you guess that the black holes start at some particular distance away from each other, and then you measure when they merge, then from that you could get roughly how old they are.
Mm-hmm. So another question, do black holes evaporate?
Yes, in theory. So this was a prediction, famous prediction by Stephen Hawking, that you might imagine. I told you that nothing can escape black holes, the gravity of a black hole, but that's a little bit maybe a lie. We don't actually know because it's such a weak effect that we can't detect it. But Stephen Hawking predicted that they actually glow a little bit in what's called Hawking radiation. And this is a quantum mechanical effect of how particles are interacting, quantum mechanical particles are interacting with the event horizon of the black hole. And this actually introduces some very deep questions that are very hard to answer, because Hawking radiation has some special properties. When stuff falls into the black hole, it's gone forever. You can never reconstruct information about it. But we believe, because of quantum mechanics, that information is preserved. It's conserved like mass and energy are. And so if a black hole evaporates after it absorbs some stuff which had information associated with it, the black hole eventually evaporates, but the information is never recovered. And so this is called the black hole information paradox. But it's a really incredibly weak effect. For black holes that are like the mass of our sun, or more massive, it takes longer than the age of the universe for one of these black holes to evaporate. So it's not something we're ever really going to detect, unless so this is a weird effect that the smaller the black hole is, the more Hawking radiation it produces and the faster it evaporates. So unless there are like really tiny black holes that are like the mass of the Earth, we're never going to see this. So we don't really know if it's true, but in theory, yes.
Okay. So were there some Nobel Prize awarded for the discoveries of black hole in our galaxies? Yay.
Yes, that's a good leading question. Thank you for asking it. Yeah, this year's Nobel Prize was for a lot of things. It was like black hole physics. But two of the people who awarded this year's Nobel Prize in physics were awarded it because of their observations of stellar orbits around Sagittarius A star and the discovery that it was a black hole. So it's really, really cool science.
Mm-hmm. So another question, if a star gets eaten by a black hole, does that change the strength of the black hole?
Yeah, slightly. When the black hole eats the star, it takes on all the mass of the star. And so it gets more massive and it gets stronger gravity. And its event horizon grows a bit, it gets bigger.
So how small can a black hole be?
Yeah, great. So this is a really interesting question because there's kind of several ways to answer it. So you might be thinking of this because I mentioned the Hawking radiation thing. And so this is kind of related. So you can ask, well, how small can a black hole be actually produced in nature, right? So like what processes make black holes and what's the smallest black hole that you could get from such a process? And the answer to that is we don't quite know, but it's between 2 and 5 solar masses, or times the mass of our sun. And the reason for this is that black holes of that size are produced by exploding stars. And if the core of the star doesn't get dense enough, it doesn't form a black hole. It forms this other thing called a neutron star, or even this other thing called a white dwarf. And so it turns out that to be dense enough to form a black hole, it needs to be more massive than roughly 2 solar masses. But we've never observed any that are that are between 2 solar masses and like 5. And that doesn't mean they don't exist, it means we haven't seen them. So but it could be that there's a physical reason behind why we haven't seen them, in which case that could be the lower limit. So that's one way of answering your question. But there's another way of answering your question, which is, well, how small would the laws of physics allow us to make a black hole? Like maybe we design a super powerful accelerator or something. Like, you know, people were afraid of this, in fact. And we could form a black hole by like mashing enough mass together by hand and thus make like an Earth mass or a moon mass black hole. You could do that. And if you had an Earth or a moon mass black hole, the amount of Hawking radiation produced would be a lot. Like people have suggested that you can make like spaceship engines out of them. But eventually, the Hawking radiation will become so strong that the black hole will immediately evaporate as soon as it's formed, because the Hawking radiation is stronger the smaller the black hole is. And so that means that you probably can't create a black hole that's you know, less massive than a couple molecules or something like this.
Okay, so what is it about particles borrowed from energy degrading black holes?
Okay, so I think this question is why does, and correct me if I'm wrong, and ask for clarification. I think this question is asking, why does this quantum mechanical effect produce this Hawking radiation? So what's actually going on here? And there's sort of 2 ways of describing it, and I'll try to describe both of them. And probably both of them are not going to be very satisfying explanations, but you know, we'll do our best. So one way of understanding this is that, well, actually, this is key to both ways of understanding it. Empty space isn't empty. So you may have heard of this idea called the Heisenberg uncertainty principle. And what it says is that you can't know the position and velocity of a particle at the same time. Well, it turns out that you also can't know the energy of a particle if you precisely know its position. And so what this means is that empty space is kind of constantly bubbling with particles appearing and disappearing, being created and destroyed, just being allowed by the fact that we're uncertain about whether or not what the energy is there. It could be 0 or it could be not 0. And so for moments in time, just moments, particles are allowed to just come out of nothing and then disappear. So what happens if this happens near a horizon? Suppose a pair of particles bubbles into existence, but one of them is behind the event horizon and one is not. The one that's behind the event horizon falls in. The one that's not flies out. That the particle that flies out makes up Hawking radiation. That's one way of explaining it. Another way of understanding it is through what's called this idea that I just described of this bubbling of space-time. It turns out that the bubbling depends on how fast you're accelerating. So if you sit still, it's maybe a low simmer. If you accelerate, you can make it a boil. And if you think about black holes, it turns out that if you're just a little bit above the surface of the black hole, well, actually this is true of Earth too, right? The Earth is pushing up at us. There's some amount of gravitational, there's an acceleration due to gravity. If you just fell off a building and you fell, you'd accelerate towards the Earth. Alternatively, you can imagine that to stay still, you have to accelerate away from the Earth. And this is called the equivalence principle. And if you just try to hover above a black hole, some distance away from the event horizon, because according to the equivalence principle, you are accelerating away from that black hole. And if you accelerate away from the black hole, this bubbling effect becomes a boil. And so then you see particles. And those particles are the Hawking radiation. Is that, I know it's not, that may not be a very satisfying answer, but if you want more, if you want to talk about it more, just ask another question and we can try and clarify.
Yep. So if you have more questions, please type into the chat channel. So meantime, maybe I can ask really spooky question. What is it inside of the black hole? Like what I can see inside of the black hole?
Yeah. So there's two answers to this again. Well, there's one, the real answer is we don't know because we can't see what's inside a black hole. It's kind of forever a mystery. But we can theorize. So there's sort of two answers here. One is what the mathematics tells us, which is that there's a point at the center of the black hole where space and time break down. It's a point of infinite density and infinite gravitational strength, and this is called the singularity. But that might not be an indication that space and time break down so much as an indication that our math has failed us. There are other examples of this where you look at something and it seems to be infinite, but it turns out that that's just because you're using the wrong math. And this is perhaps one of the strongest indications for why we need something, where we need a theory of quantum mechanics that incorporates general relativity. It's called quantum gravity, so that we can better understand with more advanced mathematics what's happening there, where things get really hot and really dense at the center of a black hole. But my conjecture is that that's what's inside a black hole is just that. It's just some extremely hot, extremely dense stuff that's sort of sitting behind the horizon, bubbling away. And what that looks like, I don't know. It could be a completely new form of matter. It might require weird and crazy distortions of space and time. It might describe the idea that space and time are something that you can just step through, so-called a continuum. That might break down. Maybe at the smallest scale, space-time is a grid or something. There's lots of ideas about this, and we really don't know. It's one of the biggest open questions, I would say, in all of physics.
Mm-hmm. Okay, so if I understood correctly, white dwarfs and quasars would be black hole if they had more mass. Is this correct, or did I miss the mark?
This is mostly correct, but I think by quasar here you mean neutron star. So quasars are these quasi-stellar objects. They're a fancy name for the supermassive black holes at the centers of galaxies. White dwarfs and neutron stars, you're exactly right. So they are less massive than black holes, and therefore they have enough sort of pressure built in them that they can withstand their own gravitational pull. But if you add enough mass on top of a neutron star, it will collapse into a black hole. And it turns out if you add enough mass on top of a white dwarf, it will collapse into a neutron star. So what's happening here is that each one of these white dwarfs and neutron stars are each held up by forces in the materials they're made of. White dwarfs are mostly made of electrons, and they're held up by what's called the Pauli exclusion principle, the unwillingness of electrons to overlap in physical space. Neutron stars are made up of neutrons, and they're more dense than white dwarfs, and they're held up by the strong nuclear force. They're essentially just like giant atomic nuclei, the mass of the sun. But if you put enough mass on there, even the strong nuclear force that holds together atomic nuclei can't support them anymore, and they collapse into black holes.
Okay, another question. How does one mine energy from a black hole?
Yeah, great. So what you do is you find a spinning black hole, preferably one that's spinning very, very fast. And you take a rocket ship or something, or a piece of metal. You can even do this with lasers. You take it and you bring it really close to the black hole. Not past the event horizon, you don't fall in, but really close. Close enough that you can pick up the rotation. The pull of its spin pulls you with it. And you start to rotate around it, whether you like it or not. And as you're rotating around this black hole, you give yourself a boost. You fire your rockets, you throw some shit into the black hole, excuse my language, you throw some stuff into the black hole, and you escape. And when you do, you carry with you all the speed that you picked up while rotating the black hole. And that speed is energy. You can utilize it. And so if you capture that motion somehow, like a generator might pick it up from you might imagine like a giant windmill picking up these rocket ships that are being thrown out by a black hole and being spun by them. For example, you could power something.
Okay, another question. How far away from the Earth is the closest black hole?
We don't know the answer to that because we don't know what the black holes are. We don't know what the closest black hole to us in our galaxy is, I would say, because they're kind of hard to find. Obviously, there's obviously Sagittarius A star that's in our own galaxy. I don't know if there are any X-ray binaries in our own galaxy that we've observed. There must be. I will look that up while I answer other questions, and I'll see if I can answer that for you.
So another question is, can neutron stars merge to form a black hole?
Yes, they can. In fact, they probably did. So in 2017, you might have heard of this thing about like this neutron star merger event where all the gold in the universe was formed or something like this. Probably what happened there is there were two neutron stars that were orbiting each other, and their orbits decayed and they merged. And a lot of amazing stuff happened when that happened. But one thing that probably happened at the end of that is that the thing that they formed was too heavy to be a neutron star anymore. And it probably collapsed into a black hole.
So another question is, why are black holes hard to find?
Yeah, excellent. So how can we see them? I talked about a lot of ways that we can see them, right? We can see them by the glow of the stuff that falls into them. We can see them by the ultra-relativistic jets that they shoot out. And we can see them by the orbits of stuff around them. So you have to find you can't just look for an isolated black hole. An isolated black hole with no stuff around it will be impossible to see because it won't produce any light. It's basically invisible. But a black hole that has stuff orbiting it or stuff falling in, that we can see. So that's why they're hard to find. Okay, so I found it. There are roughly 200 low-mass X-ray binaries in our galaxy that have been detected. So I would say that means that there is roughly, what's the diameter of our galaxy? Divide that by 200. That's probably rough. Well, that's That's not, no, that's wrong. I don't know what the closest one is. I'll have to look still. But there are certainly several in our galaxy that have been seen.
So can light be bent enough around the black hole so that we can see an image of ourselves?
Let me think about that. So I think what you're asking is, like, the sun is shining light off of us, or shining light onto us, and some of that light is reflected off of us, and it's going to go into space somewhere, and it might pass by a black hole, and the black hole might bend it all the way back around to point back at us. Yes, that could happen. We won't. The optics probably don't work out that we could see a real image of ourselves, but a photon that bounced off of you could go all the way to a black hole, bend around, and then come back to where you were. Of course, you would never know that. You'd be long dead by the time that photon got back to you, because it takes time for black holes to, or it takes time for light to travel. Light travels at the speed of light, which is something like, I don't know this number in miles per hour, but it's 100 million meters per second, 300 million, in fact. And that means that, you've heard of a light year. That's the amount of time it takes that's the distance that a light can travel in a year. Okay, yeah, and I found it. The closest black hole that we've observed is 8,000 light years away from us. It's Cygnus X1. So light years are very, very big, and the closest star to us is 4 light years away. So it would take 8,000 years for light bouncing off of you to reach the closest black hole we know of, which is Cygnus X1, and then another 8,000 for it to come back. So if you live 16,000 years, you could maybe be irradiated by the photons that bounced off of you.
Could we see an image of our Earth 50,000 years ago?
Oh, that's a cool idea. I'm going to answer that several ways. One is that no, because the light that bounces off of the Earth and then goes to the black hole, it's going to spread out and dissipate, and the optics just aren't going to work out. You'd need like a lot of lenses between here and the black hole to make that work. But in another sense, kind of. We can't see Earth from 50,000 years ago. But if we look out and we see another planet 50,000 light years away, that planet might look like Earth. And so in many, this is kind of one reason that it's so exciting to look for exoplanets, which is something I haven't talked about, right? Is that exoplanets are in many ways a lens into our own past, the past of our solar system, or if we're really lucky and if we look out in space and we see a planet that's like got air or water on it, then maybe a lens into Earth's past itself.
Okay, so another question, can black holes get so full of matter so they can't absorb anymore?
No, they can grow without bound, as far as we know. That's entirely true. I think that's true. I don't think there's any limit to how massive they can get.
Okay, so yeah, another comment, maybe you said this, regarding the black hole at the center of our galaxy, how large it is if its size is defined as the diameter of its event horizon?
Yeah, I did not say that, and that's an excellent question. So It's roughly a million times. This is going to be, you can look this up if you want the precise details, but I'm going to try and I'll look it up for you as I talk. But it's roughly the mass of our sun. I'm sorry, 6 million times the mass of our sun. And it turns out a funny fact of these black holes is that their diameter is directly related to their mass. So if you double the mass, you double the diameter. And this is really different from how, for example, stars, like the radius of a star or the Earth, if you double its mass, you don't double its diameter. The relationship is different, more complicated. And so I looked it up. Sagittarius A star has a diameter of 27 million miles from one end of the event horizon to the other. So it's pretty big. But what's kind of crazy is that Sagittarius A star, one weird thing that happens for these really supermassive black holes is that if you measure like the mass divided by the volume, it's really low. So like somewhere deep inside Sagittarius A star, I'm sure it's very hot and dense. But if you pretend that all the mass of Sagittarius A star is sort of evenly distributed throughout the black hole, it's less dense than water.
Mm-hmm. So another question, what happens to a black hole that somehow exceeds the rotational breakup speed?
There is no rotational breakup speed for a black hole. I mentioned this limit, but this is a great question. So I mentioned this limit of, I called these black holes extremal, where it's not so much that it's so fast, it's rotating so fast that it's going to break up. It's rotating so fast that all the material, all the energy in it is rotational energy. It's like not the amount of material compared to the amount of like rest energy coming from the mass compared to the amount of rotational energy is infinitely, it's infinitely more or infinitely less. And these extremal black holes are really strange and probably can't exist because they get they lose their event horizon and you can just go in and out of them. So they're very weird. In a real physical black hole, actually something quite interesting happens, which is that as you spin the black hole up, which can happen by dropping stuff in at an angle, the same way that you can spin something up by hitting it at an angle, you can figure out that as you do this, you're adding both mass and angular momentum at the same time. And so the most quickly that you can spin a black hole is defined by this parameter, which is the ratio of angular momentum to mass, which is called the spin parameter. And the highest you can get it is something like 0.97, which is incredibly fast. I mean, it depends on the mass of the black hole as to how fast that actually is, but it's super relativistic speeds.
So another question is, what is the biggest black hole discovered so far?
Oh, this is something I really should have looked up before I gave this talk because that would have been a cool fact. I don't know the answer. They get much bigger than Sagittarius A star. Sagittarius A star is a baby compared to some of the most massive supermassive black holes. They get so big that we don't have names for their masses anymore. The most massive ones are something like 10 to the 10s times the mass of the sun. So that is 10 billion times the mass of the sun. Apparently, I think there's one that is 60 billion times the mass of our sun.
Any more questions? Okay, goofy question. Is it currently known if a black hole has a backside where all the stuff sucked in comes out? Is there a chance we one day find out?
Not that we know of. So this is the idea of a white hole, right? Like stuff that goes in one end of the black hole, goes into the black hole, gets sped out through a wormhole somewhere else through a white hole. It's probably not real. Probably the stuff that falls into a black hole just stays there.
Okay, so another question. Can black holes suck themselves up?
Yeah, so this is, I don't think so. It's kind of hard to define what the word, like what it means for a black hole to suck itself up. But, you know, the event horizon is a weird thing, right? It's not really the surface of a black hole. It's the place where if you get any closer, you can't escape anymore. So it's the surface really of the black hole is somewhere further deep inside, and we really don't understand. We don't know what's going on there.
Okay, any more questions? Wait a minute or two. So maybe meantime, since we are in the Halloween, so what do you think that it will be really cool for the next black hole physics you want?
Oh, that is a great question. So it depends on how speculative I'm feeling, I guess. What I'd really like to see, which is getting less and less likely, is some indication that that general relativity breaks down outside of a black hole. So one thing that would be really amazing, or alternatively, that black holes can interact with, in some way with dark matter. So there's this idea of dark matter orbiting black holes in orbitals, kind of just like electrons orbit an atomic nucleus. And this can do all sorts of really crazy and interesting things, assuming it works out. Like you can spin down black holes because the dark matter can mine them for energy, like by the Penrose process that I described, or they can like oscillate and produce gravitational waves. That's really speculative, but it'd be really cool to see something like that. More realistically, I think the next black hole physics that's going to be really exciting and that we're going to really learn more is, I think it's going to come from the Event Horizon Telescope. I think as the Event Horizon Telescope does more observing and gets better at this, at some point we are going to be able to, that fuzzy image is going to be much better resolved, and we're going to be able to ask really interesting questions about, like, is the event horizon shaped the way we think it should be? What is the plasma of the gas doing as it falls into the black hole? I think that's coming in the next 10 years or so, and it's going to be really awesome.
Thanks. So any more questions? Final call. Okay, if not, so those are all the questions that came from the attendees. So Jonah, thank you so much again for sharing with us tonight. So everyone have a spooky Halloween and join us next week to learn what to look for in the night sky in November. So find this event information and others on the PEEC website, peeknature.org/events. So thanks again for tuning in. Good night, everyone, and happy Halloween. Thank you.
Thanks for